In this video, I'm going to discuss thin film interference. So first we need to look at the idea of superposition. So we discussed superposition when we learned about waves. So when a wave is reflected off of a surface, okay, or a rigid fixed surface, the wave actually inverts itself when it reflects back. Okay, so how can we look at this in terms of light? This is how we looked at it in terms of, mechanical waves. So we see that superposition, like here it's going up, and then when it reflects off, it is inverted upside down. Now, in terms of light waves, this can also happen. We call it a phase change. A phase change is when it inverts itself by what we say at like 180 degrees, okay? So now the crest and the trough are sort of inverted from one another, okay? If a light ray strikes a more dense medium and reflects off it, so a medium where N1 is less than N2, then we see a 180 degree phase change. So we see the superposition occur. Now, if we look at this example, this is when we look at a free support. So this is not fixed. This wave can, the end of the rope here can move as the wave goes here. We actually don't see that superposition when it's reflected back. It maintains its same direction. So in terms of light, this happens when light strikes an interface between a medium that has a lower index of refraction to one that has a greater index of refraction. So if you're going from a more dense to a less dense medium, then we don't see a phase change, okay? And the wave reflects back the same way as it encountered the medium, okay? So this is important because this is what leads to interference effects in thin films. So a thin film is just a thin medium that's over the surface or in between two surfaces. So some examples are like oil on water and bubbles. So if you look, you can see that sort of iridescent color. That's because of interference that is happening within the bubble. So the soap is the thin film, and then you have a medium on the outside that's air and a medium on the inside that's air. Over here, when we look at an oil slick and you see those sort of color patterns, those rainbow patterns, the first medium is air, the second medium is oil, and then underneath the surface of the oil is water. So we're going to look at why sort of these shiny patterns happen, okay? And it's important to note that when we look at these interference patterns, we are assuming that the light is striking essentially normal to the surface, although that when we look at it, it won't be perfectly normal. Okay, and remember, normal means perpendicular. Okay, so a couple of things that we need to remember. So what I just said about the phase change. When we go from an N2 that is greater than an N1, so when we reflect off a more dense medium, there's a phase change. When you reflect off a less dense medium, there is no phase change. The other thing that we have to recall is from the refraction video. So as light enters into a new medium, it actually changes its wavelength. And the new wavelength within the medium is equivalent to the original wavelength divided by n, the index of refraction of that medium. So keep those two things in mind as we go forward here. So here's an example like the bubble, right? So we have air here, we have the film of soap, and then you have the air, okay? So light strikes the surface of the bubble, and some of that light is reflected off of the surface. Now, because it's going from a less dense medium to the more dense medium of soap, we're going to see a 180 degree phase change. The light inverts itself when it reflects here. Now, the light that then is refracted through the medium, as it strikes the interface between the bubble and the air, this is going from a more dense to a less dense medium, or where N1 is greater than N2, so we see no phase change. And when this escapes here, you're going to have one light that has a phase change and one light that has no phase change. So if you imagine they arrive at some position, you could see some destructive interference there. But it's all relative to how far the light waves have to travel, correct? So the thickness of the film plays a role in how far the light has to travel. So we can actually calculate the interference that is going to happen some distance away. So in order to calculate this interference, we have to note that the second ray is going to travel a further distance, right? It's going to travel 2t. So if we look back up here, t is the thickness of the film. And again, remember that we're assuming that it's striking normal. So even though we see an angle here and we know that this distance isn't exactly t, we just assume that it's very close to t. So the distance that light ray travels further is 1t down and the 1t back up for a total of 2t. So in order to see constructive interference patterns for this case of a thin film where you go from, air to soap to air, the equation is that 2nt, or twice the index of refraction times the thickness, has to be equal to m plus 1/2, so the order number plus 1/2 times the wavelength, okay? So remember that this is plus 1/2, and the reason is because one has phase changed and one has not. So they need to arrive at some distance away, a half a wavelength off, in order for them to be in phase with one another and constructively interfere. Where this n comes from is taking into consideration the change of the wavelength as we enter into the new medium. So that whole wavelength in the new medium being equivalent to wavelength over n. Now for destructive interference for this case, it's just going to be 2nt equals m times the wavelength. And that's because, remember, that they are already out of phase when they escape. So if we look at this, they are already out of phase when they escape. So if they arrive at some position having traveled the same distance or some distance that's relative to the wavelength, then it will destructively interfere. Now let's look at a case that's like the oil. I'm going to skip past this slide. So in this case, we're going from air to, and this is giving an example of a solar cell, but it's similar to the oil idea. You've got air, and then you've got silicone monoxide, and then you've got silicone. So there are 3 layers, and the index of refraction actually increases as we go down. So again, just like in the last example, as the light ray strikes the surface, there's a phase change because we're going from a less dense to a more dense medium. Then some of the light that's refracted here comes through, and it's going to again encounter an interface where you have a less dense to a more dense, or where N2 is greater than N1. So you're going to have another phase change here. So what that does to our rays is that when they both escape and head towards your eye, which would be over here somewhere, they're in phase with one another. So it inverts the equations. In this case, constructive interference occurs when 2nt equals m times the wavelength, because they're in phase with one another. And destructive interference occurs when you have 2nt being equivalent to m plus 1/2 of the wavelength.